Let's do an introduction to hardware in the loop testing, or hill testing in short. I will cover both the setup of hill systems as well as best practices for controller hill testing. Let's look at a hill test setup. There are typically two main components. First, your controller under test. This includes both the production hardware and the embedded software that requires thorough testing. And second, a hill test system. The hill system is composed of a real-time simulator that runs a digital twin deterministically, together with I/O modules that ensure low latency data acquisition, signal conditioning, and communication with the controller under test. The host computer runs dedicated application software that supports you on the setup and operation of the real-time simulator. Depending on the size of your group and how you organize development of embedded software, the hill system setup and controller hill testing can be done by the same or different teams. Let's assume our embedded system group is segmented into three. Simon's team focusing on assembling and setting up new hill test systems. Sophie's team in charge of running embedded software test campaigns, and Corinne's team who is tasked to develop and revise the embedded software. So the question is, how are we enabling these teams to succeed in their specific task? Simon has previously built a hill test system based on the Speedgoat performance machine. Simon's team is now challenged to specify a new, much more complex hill test system, which is required to integrate high-power actuators and electronic loads and sources. Implementing such a hill system is time-consuming and requires specific expertise. With that in mind, Simon has decided to rely on Speedgoat's know-how to provide him with a modular, rack-mounted hill solution customized to his needs. The final solution looked as follows. Two rack-mounted performance real-time machines enabling distributed and synchronized simulation across multiple chassis. This setup fully integrates all power electronics components, the required signal routing and conditioning modules, as well as breakout panels and the cabling harness. For Simon's team, this is a true plug-and-play solution. With hardware hurdles off the table, the team was able to focus on the design of the digital twin and even introduced some innovations. For instance, model parameters are now automatically fine-tuned to fit measured data. Connectivity with the controller was also done very quickly with a simple drag and drop of Speedgoat driver blocks. Using Simulink Realtime, the model ran on the Speedgoat machine with a simple click, and the team could verify correctness of all interfaces right from Simulink. The hill system was instrumented with MATLAB's built-in app designer. User interface controls directly connect with the real-time application, allowing the hill system to be operated independent from Simulink. In parallel, Sophie's team has been creating scripts to batch and optimize test workflows. Part of the team has been using Simulink Test, which has shown to be a great asset worth of its investment. For instance, most of the desktop simulation tests were reused in the real-time runs. Real-time test campaigns were triggered with just a few clicks, and the assertion of results was fast and easy using inbuilt visualization tools. Besides, detailed test reports could be generated automatically. This greatly simplified communication with Corinne's team and helped further expediting software revision work. All in all, the group was able to quickly resolve several critical errors and run all test campaigns without damaging any hardware. By using the right tools, the team could shield itself from many test trivialities and focus on what was truly their mission, which is develop outstanding controls.